Thanks heaps for the question, Eva. Hopefully I can help explain it to you now. So, this is what we're looking at, and we had to explain why sulfur had a lesser first ionization energy than phosphorus. And kind of the confusing part here is that sulfur actually has a greater number of protons and electrons than phosphorus does. And if you just knew that fact alone, you would probably predict that sulfur actually has a greater ionization energy. Because if we remember, the ionization energy represents how much energy is needed to break apart an electron from its atom, right? And so if we have more protons, so that's what I drew here in this middle here. So this is a nucleus with a bunch of protons. If I increase the number of positive charges here, and we've got electrons around the edge, there's going to be more of an attractive force between the negative and positive charges. And that's going to make it more difficult for an electron to break away, because they're going to be more attracted to the positively charged proton. So greater electrostatic force means it's harder for the electron to break away. So that's the hypothesis of why sulfur should, quote unquote, have a higher first ionization energy. And I should also mention the other concept is screening here. And so screening refers to actually how many electron rings are between the outermost valent electrons and the nucleus. And it's the same here. They're only separated by one here in the periodic table. So what we need to do to separate these and distinguish between their ionization energies is to look at our shells and our orbitals. And so what I've written here is the base configuration of both of these. So notice as 2, 4, 10, 12. So 12 electrons gets us up to the 3s2 subshell. But then we actually have to go in here to get up to 15 and 16 respectively. We have to dive into the 3p orbital. And this is where we'll notice a bit of a difference. So we've got 12 here, all up, 12 here. To get to 15 we need 3 more electrons. Hopefully you can recall that in the p orbital here, 3p, we've actually got 3 separate kind of groups or pairings of electrons within the orbital. And there's a rule here which tells us that if we have 3 different boxes to fill, or 3 different suborbitals that we can fill with electrons, if you're given just 3 electrons, it's going to configure as 1, 1, 1. They're not going to go like 1, 2, 1, and then have this guy blank, right? And that's for stability. So if we look at phosphorus, this is what we're going to get for our 3p suborbital. We can denote this as like subscript x, subscript y, subscript z, but that's not the important thing here. The important thing is that we've got 1 electron in each of those subsections. Comparing that to what we need to do to just get 1 more electron, right? 1 more electron, there isn't another box here for it to fill. So now we can come back to the initial box and we can put 2 electrons in. And so it'll look like this, right? But now in the sp subscript x, so this is a suborbital, we've got 2 electrons. And what that means is that we've got 2 negative charges. And similarly when we were talking about with the positive attracting the negative here, and that causing electrostatic attraction, we've actually got repulsion here. These 2 electrons are going to have some sort of like repulsive force away from each other, which actually means that they're less closely bound together and thus easier to break apart. it's actually much harder to take a single electron here than it is to take one out of this lone pair of electrons, or lone pair in terms of orbitals. So yeah, so that's why sulfur would have a slightly lower first ionization energy than phosphorus, and it's about the grouping of orbitals in the 3p subshell. So I hope that helps, and let me know if you got any questions. Thanks, Eva.